Welcome to Fatigue Analysis. I'm Dr. Stewart, and today we're going to do an example for variable amplitude loading. This is example 2. In this example, we're asked to use a nonlinear damage rule to estimate the total damage accumulated in a single repetition. We're given this 4-stepped fatigue test where each step is occurring at a different stress amplitude, and we need to figure out how much damage is accumulating and adding from 1 to 2, 2 to 3, and 3 to 4. We're given the following information: a table that describes the 4-step test where each step is at a different stress amplitude, and let's say that is in megapascal, a different number of cycles, and a different number of cycles to failure of the material at that stress amplitude. We also are given the following nonlinear damage rule, where di is equal to the cycles in I divided by cycles to failure in IF to the power alpha I. And where, if we were to actually put iterations, so replacing I with 1, well, di would be equal to little n, 1 divided by cycles to failure at 1, and then damage 2, d2, would be equal to n2 divided by cycles to failure in f2 to the power, so this is what the alpha parameter means, which is the cycles to failure at 2 divided by the reference level of cycles of failure at 1 to the power 0.4, right? So this rule here, we are going to use iteratively to calculate D1, then the effect to D2, the effect to D3, and then finally the damage at the end of that 4th step. So let's go ahead and get started here. Our knowns and unknowns, we know that there are 4 steps. In MathCAD, we're going to set the origin of our arrays to 1, so we iterate from 1, 2, 3, 4, instead of starting from 0. And we're going to take that table and turn it into MathCAD vectors so that we can more easily use those numbers. Our solution, what we're going to do is apply the nonlinear rule 1 step at a time. And our goal is to construct the damage curve by letting the damage from the lowest level, from step 1, serve as our reference. So let's start with calculating the damage at step 1. D1 is equal to N1 divided by NF1. So the damage accumulated at the end of that first block, or at the end of the first step, is going to be equal to 0.01. Now what we need to do is use this result, the damage at D1, and use it as a reference to find the equivalent damage as if we were conducting our experiment at the rate of step 2. So we need to find like an equivalent damage as if we were loading at the same stress amplitude as the 2nd step, right? So how do we do that? Here we're illustrating, say we have 2 completely separate fatigue tests. One that's run at the first step's stress amplitude, and another one that's run at the 2nd stress amplitude. So these are 2 independent fatigue tests. What we're doing when we're applying this nonlinear rule is we are normalizing by the cycles to failure in both of those independent experiments, and then we're finding an equivalent damage. So we're taking the path for the first step's damage up to its cycles to failure, and then we are trying to find what is the equivalent damage if we moved in a dotted line across to the stress level of the 2nd step. And then we will continue to accumulate damage from there, right? So we have to find this effective damage shift. And we'll do it by finding something called N equivalent. The equivalent, we call it N equivalent. Here it's N to F. So we're going to find that, and then that is going to help us to say how much damage would have accumulated at the 2nd step. What is the equivalent damage? So in step 2, the damage accumulated in step 1 is going to be added to step 2 by finding this equivalent damage NEQ. So let's solve for this equivalent damage NEQ, where we'll assume we'll initialize it as a value of 1. We'll create a solve block where we give that the damage in the first step is equal to this equivalent damage over the cycles to failure at 2 to that alpha power, NF2 divided by NF1 to the power 0.4, right? So in essence, we're making that vertical line here by finding this inequiv. So we've got the solve block, we're given that, we're saying that it must be equal to this, and then we're finding what it should be, and it's going to be 1.599 times 10 to the 3. So this inequiv is the number of cycles at the second stress amplitude that would produce an equal amount of damage to that we obtained at the first stress amplitude. So now we're at the right point to continue to add up the damage. So now we can calculate the damage accumulated in step 2 by taking the prior damage from step 1 plus the number of cycles at step 2 to get damage at 2 equal to 0.012. All right, where we've added the effective damage from sigma 1 using NEQ, and that will accumulate to give us D2. Now we just have to repeat this process for every step. We'll repeat the process of finding equivalent N, so NEQ, and advance our damage state. So in step 3, let's say NEQ, we're just going to initialize it as 1,000. This is an initial guess. We're given our solving block equation here, where now we're having the value of D2, and we're saying that there's an NEQ we need to find for step 3, and we find that NEQ is equal to 4.938 times 10 to the 4, right? So now we know what is the equivalent damage at the third stress amplitude. We then plug that in together, so the damage that's accumulated from step 2 and 3, that's what this NEQ is here, plus the amount of damage we're actually going to accumulate at step 3. So now D3 is equal to 0.013. All right, and now we do our final step. We're repeating the process, finding what is the equivalent damage at the fourth step. That includes the damage of all the prior steps. We initialize NEQ at just a number that is large here, just an initial guess. We're given, again, our solve block here, where we say that the damage D3 that we stopped at, we want to find the equivalent damage at the fourth step's stress amplitude, or the fourth step's conditions. We find that the NEQ is equal to 7.611 times 10 to the 5, and then we put that damage, so this NEQ represents the prior damage from the prior 3 steps, plus the damage that's accumulated for the fourth step to give us D4 is equal to 0.016. So now we've solved our problem. We've found how much damage has accumulated from step to step, how it added up to give us our current damage state. Now, a way that we can visualize this to kind of make it make sense a little bit better is this little sketch here, where we plot damage versus cycles to failure. We can see that we have lines that represent each of the steps, step 1, 2, 3, and 4. If they were independent, separate, completely separate fatigue tests, they would have damage rate accumulation curves like this, right? In essence, what we are doing is we are creating a step test where we're taking the damage that accumulated in step 1, and then we're finding what is the equivalent amount of damage at step 2, if it was performed at step 2, and then we're going to add how much we've accumulated at 2 together. So the NEQ plus the the lowercase n2 gives us D2, and then we find an NEQ for D3, and then we add the N3, and then so on and so forth to add the effect of prior damage to the current damage state. So that is pretty much this example. It takes a little bit of work for us to add these damage terms up And typically people would write a program, like a C program or a MATLAB program, to do this kind of stuff more efficiently. All right, so that's the end of this example, and I'll see you in the next video.